Welcome, focused learners. If you are gearing up for your exams, especially tackling something like the Cambridge Additional Math syllabus, you are in exactly the right place. Today, we are diagnosing and curing a really common issue, looking at an equation and having absolutely no idea what it actually looks like. We are building a bridge, specifically the visual to algebraic bridge. Our goal today is to totally demystify quadratic functions by connecting abstract algebra directly to visual geometry. Instead of just memorizing rigid formulas, we're going to learn how to literally see the math. If you've ever stared at a string of x squareds on an exam paper and wondered what it actually means in the real world, stick around. Oh, and before we really get going, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. All right, let's get into it. Here is our quick roadmap for today's session. We'll start with the origins of modern algebra, move into the anatomy of a parabola, and then master finding the turning point. After that, we'll decode the discriminant and wrap up with intersections and inequalities. Section 1. The origins of modern algebra. Let's see where this all actually started. Now, you might think this math has just been around since the dawn of time, but the modern way we write it is a relatively recent invention. We are going to anchor our entire strategy today on this absolutely brilliant quote by the 18th century mathematician Sophia Germain. She said, "Algebra is but written geometry, and geometry is but figured algebra." I love this so much because it highlights the direct, undeniable translation between the formulas on your paper and real-world shapes. They aren't two separate subjects you have to study. They are just two different languages describing the exact same truth. Today, you are going to become a fluent translator between the two. And this image right here brilliantly illustrates our historical roots. This is François Viet, a 16th century French mathematician. What's incredible about Viet is that he was actually a lawyer by trade, serving kings of France, but he completely revolutionized math by starting work on what was called the new algebra. He was the absolute pioneer who introduced the innovative use of letters and parameters into equations. I mean, imagine doing high-level Cambridge math where you had to write out everything in long-form words instead of just using a letter like X. No thank you. He laid the groundwork that allows us to quickly decode these shapes today. Moving on to Section 2, Anatomy of a Parabola. Let's break down the actual shape. Let's get our foundational definitions crystal clear. First up, a polynomial. This is simply an expression where the variables have positive whole number powers. Simple enough, right? But our star today, the one you'll see constantly, is the quadratic function. This is a polynomial where the highest power of the variable is exactly 2. So you'll see an x squared, but you will absolutely never see an x cubed or an x to the power of 4 in these functions. That little exponent of 2, that is the boss. It dictates everything we are about to see. So the absolutely crucial point here is that just by looking at the sign of that x squared term, you immediately know the geometry of your curve. If the x squared term is positive, it completely dominates the expression when you plug in large numbers, pulling the ends of the graph infinitely upwards to create a U-shaped curve. This means the graph has a valley, or what we call a minimum turning point. Conversely, if that x squared term is negative, it drags the whole graph downwards into an N shape, giving us a peak or a maximum turning point. Literally, with one single glance at the first term, you've already decoded the overall shape of the equation.
All right, Section 3, Finding the Turning Point.
Knowing the general shape is a fantastic start, but to grab those top marks, we have to explore how we mathematically pinpoint the exact peak or valley of that curve. Now, often, we can find a turning point by finding where the curve crosses the horizontal x-axis, its roots, and just finding the exact middle point between them. Easy. But I want to pose a much more practical exam challenge. What happens if the curve just hovers above the axis and never actually crosses it? Our standard method of factoring completely fails here. We need a much more powerful algebraic toolkit. Enter an incredibly elegant method called completing the square. We can follow these exact steps to convert any standard quadratic expression into a much more revealing format. First, you take the number sitting in front of your single x, and you have it. Second, you square that result. Third, you use that number to break up your original constant term. And finally, you rewrite the whole thing as a variable plus a number, all squared, plus whatever constant is left over. I know, it sounds like a bit of algebraic gymnastics, but stick with me, let's see why it's so amazingly useful. Oh, and real quick, if you're finding this breakdown helpful, make sure to subscribe to our YouTube channel Ace the Exams at acexams_IGCS to excel in your Cambridge examinations. Okay, so back to our newly completed square format, which looks like this. Open bracket, x plus a, close bracket, squared plus b. This is incredibly powerful. Why? Because think about it. Any real number, when squared, is always 0 or greater, right? It can literally never be negative. So the absolute lowest value that squared bracket can ever possibly be is 0. When that bracket hits 0, you are left with just the constant b at the very end. The geometry of the curve's minimum or maximum value is perfectly, beautifully exposed by the algebra. The exact turning point is literally staring right at you from the equation. Moving right along to section 4, decoding the discriminant. So sometimes you don't actually need to fully solve an equation. You just need to diagnose how it behaves. Think of the discriminant as your ultimate mathematical decoder ring. If you remember the famous quadratic formula, the discriminant is that specific little part sitting entirely under the square root, b squared minus 4ac. Because it lives under a square root, it dictates the visual graph instantly. If that value is greater than 0, well, you can take a positive and negative square root, meaning you get two distinct answers. Geometrically, the curve crosses the horizontal axis twice. If it's less than 0, you are trying to take the square root of a negative number, which gives absolutely no real roots. Geometrically, that means the curve just floats entirely above or below the axis, never touching it. And this brings us to the most unique scenario, the one examiners love to test. What if that discriminant is exactly 0? Well, the crucial point is that the square root of 0 is just 0. You don't get a plus and a minus answer, you just get one single repeating root. Visually, this means the curve comes down, perfectly grazes the x-axis at a single point, and sweeps right back up. It touches it, but absolutely does not cut through it. And finally, section 5, intersections and inequalities. Let's see how all of this builds into solving those dynamic high-mark scenarios where different mathematical shapes actually collide on the graph. So far, we've only looked at curves interacting with a flat, horizontal axis. But what happens when a diagonal straight line meets a curved parabola? Do they crash into each other? Do they miss entirely? To solve this algebraically, we simply substitute the linear equation of the straight line directly into the quadratic equation. By setting them equal to each other, we create a brand new simultaneous equation. Once you combine them into one single quadratic equation, all those exact same rules we just learned apply again. By evaluating the new discriminant of this combined equation, you can instantly visualize the collision. If the discriminant is greater than 0, that straight line cuts right through the curve at two distinct intersection points. If it's less than 0, the straight line completely misses the curve. And if it's exactly 0, that means the straight line comes in and perfectly acts as a tangent, kissing the curve at exactly one point before continuing on its way. It is a fantastic shortcut to analyzing graphs. And this brilliantly illustrates how we can easily tackle inequalities as well. If you were ever asked in an exam to find where a curve is entirely greater than 0 or entirely less than a straight line, please don't panic. You simply map out the critical points. Those are the roots where they perfectly equal each other. Then you just test the intervals between those critical values to see if the outcome is positive or negative. You are basically just checking if the curve has dipped below the water level or risen above it between those specific crossing points. And that brings us to the end of our diagnostic clinic today. We've seen how positive and negative terms shape the curve, how completing the square uncovers the turning point, and how the discriminant acts as an instant visual decoder. We will end with this provocative thought, circling back to Sophia Germain's opening theme. If geometry truly is just figured algebra, how will you use this algebraic toolkit to decode the hidden shapes in your next past paper? The shapes are already there in the numbers, just waiting for you to reveal them. Drop a comment below with your target grade and the biggest challenge you're facing. Our team responds to every comment. And one last time, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Keep practicing, keep decoding, and I'll see you in the next one.